In gases 3, I'm going to go over 3 gas laws that are predicated on the gas properties we've discussed in the last 2 videos. First is Boyle's Law. This is named after Robert Boyle, who was a scientist who experimented with volume and pressure. Now, what Robert Boyle found was that if you hold temperature constant, the volume that is occupied by a fixed mass of gas, so the same sample size, the same number of moles, is inversely proportional to its pressure. Now, we've explored this through a PHET simulation, but now I'm officially defining it for you as Boyle's Law. And mathematically, that can be represented here, which is showing volume is proportional to 1 over the pressure, or the inverse of the pressure. So what you can see in this animation is that as the volume decreases, the particles are colliding with the sides of the walls of the vessel more frequently, which is creating a higher pressure. So as volume goes down, pressure goes up, and that is because we have more collisions with the side of the wall. Graphically, it would look like this. This is a volume as a function of pressure, and when you graph this inverse relationship, you're going to get a hyperbola. So you're going to have a shape like this. Now, in our Georgia Standards of Excellence, they explicitly state that you are to learn how to analyze these laws and these gas properties graphically. Now, something that is important for you to understand is if we were to linearize this graph, we could graph velocity as a function of the inverse of the pressure, and that would give us a line with a constant positive slope. Boyle's law mathematically is expressed as pressure 1 multiplied by volume 1 is equal to pressure 2 multiplied by volume 2. So you can think of this as your initial conditions of pressure and volume and your final conditions of pressure and volume. But remember, this is only valid at a constant temperature and sample size. Let's do one sample problem using Boyle's Law. On a road trip out west, we bought Sophia a balloon in Oregon. The volume of the balloon was 5.0 liters at 101 kilopascals of pressure. After the long drive to Colorado, we found the atmospheric pressure was only 91 kilopascals. If the temperature was the same in both places, what is the new volume of Sophia's balloon? All right, so the key to these problems is to write down what we know. Let's look at our variables here. We have our initial pressure and volume, and we have our final pressure and volume. So we have Oregon, and then we have Colorado. What do we know? Well, we know everything except for the final volume, which it is being asked for in this problem. What is the new volume? So, remembering that volume is inversely proportional to pressure. Well, pressure has decreased. So we want to be able to look at this problem, and we should be able to put in our values. And before we even plug and chug, because these are very straightforward computations, we should be able to make a prediction. Well, pressure has decreased. Therefore, we would predict our answer would indicate that volume increases. And indeed, when we put in our variables and solve for velocity 2, we get the new volume of the balloon to be 5.5 liters. Now, notice that you do not need to convert anything as long as you're consistent. So our pressure units are in kilopascals and our volume in liters. So we're consistent, and mathematically you can see where the pressures would cancel out, giving us the unit liters. In our next law, this is Charles's law. This is named after the French scientist Jacques Charles. And he was actually one of the first individuals to ever go up in a hot air balloon. He found the values of temperature in Kelvin. Remember, we're dealing with gases here. In Kelvin, an absolute temperature scale, and the volume of a gas are directly related or directly proportional. So an example of this would be if we were to double the temperature, then the volume would double in response. Let's take a look at this animation here. We have two rigid vessels, and inside is a gas particle, and they are at two different temperatures. Looking at this one here, you can see that the red gas particle, which is at a higher temperature, it's at room temperature, 273 Kelvin plus 25 degrees Celsius, it's actually covering a greater distance at the same time. All right, so what does this mean? This means that we see, that this energy is going up. Okay, so the caveat is pressure must remain constant. Again, we've seen this through our exploration using the PHET simulation. Now, officially, this is known as Charles' Law. Now, graphically, because these are directly proportional, as volume goes up, temperature goes up, okay? And we would expect a graph that would have a constant positive slope. Officially, Charles' law mathematically is the velocity 1 divided by the temperature 1 is equal to velocity 2 divided by temperature 2. In other words, our initial volume and temperature, and then our final volume and temperature. Remember that pressure must remain constant. Let's do one Charles's law practice problem. Sophia leaves her 5.5 liter balloon in the vehicle as we are visiting a nature center. The temperature is 2 degrees Celsius. The sun comes out and heats the inside of the vehicle to 26.5 degrees Celsius. If the pressure was constant, what is the new volume of Sophia's balloon? All right, we're going to put our variables. We're going to write down what we know. We're going to figure out what we're trying to find. We want the final volume after the sun heats up the balloon. So we have our mathematical representation here. We're going to then make a prediction. And what are we seeing? We're seeing that the temperature has gone up, which is directly proportional to the volume. So we would predict, indeed, the volume will increase as a result. Let's go ahead and put in some numbers here. Let's rearrange. And lastly, let's solve for the new volume of the balloon to be 6.0 liters. The third gas law I want to talk to you is in this video is Gay-Lussac's Law. And this is named after Joseph Louis Gay-Lussac, who found that values of temperature and pressure of a gas are directly related. Mathematically, as you can see here, that as pressure goes up, temperature goes up as a result. All right, so that's no surprise there. As the temperature of the gas increases, so does the average speed and therefore the kinetic energy of the particles. Now, in the last video, we spoke about Thomas Graham's law and the rates of effusion. And we went through a derivation to show that. And in that derivation, we were looking at the kinetic energies of the two gases and comparing them based on their molar mass. So again, this should not be a surprise to hear, but I am telling you it's official. Gay-Lussac's law is mathematically and graphically represented just like we saw in Charles's law. Pressure as a function of temperature in Kelvin will give you a constant positive slope because they are directly proportional. If we look at this animation here, you can see on the left we have low pressure, low temperature. Why is it low pressure? That depends on the number of collisions that are occurring inside of the container. Now, as with the other two laws, volume, okay, we're seeing something must be held constant here. In this case, volume is held constant. Going back to the PHET simulation, remember I was able to hold certain properties and variables constant and then manipulate other ones. Well, in this one here, if you were to go back to that simulation now, and you were to heat up the sample at a higher pressure, you would have, or a higher temperature, you would have more kinetic energy and thus more collisions with the container, resulting in a higher pressure. And in that simulation, if you keep heating and adding particles, you eventually would blow the lid off of the vessel. All right, mathematically, Gay-Lussac's law, pressure 1 divided by temperature 1 is equal to pressure 2 divided by temperature 2. Mathematically, this is identical to how you would solve a problem using Charles's law. You're taking these initial, in this case, pressures and temperatures, setting them equal to your final pressures and temperatures. So for this particular law, I really didn't see any reason to do another sample problem because it would be identical to what we did for Charles's law. So based on the Georgia Standards of Excellence, we're continuing to look not only quantitatively and conceptually, but also graphically at the relationships between pressure, volume, temperature, and the number of moles of a gas. I'll see you guys in class.